Hello, everyone, and welcome to the Week 8 lecture. This lecture is going to be about conservation of energy, which if even if you didn't know it, we already talked on about a little bit. So, when we were talking about finding the kinetic energy, what we did was we talked about the force, the work done by forces on the material or on the object that was causing a change in kinetic energy. So the next step of what we're going to be doing is just to formalize what it looks like when we have a force that we're talking about, and we want to talk about the potential that it has to cause a change in kinetic energy, even if we don't talk, or even if we uh, don't necessarily go that path, it has the potential to cause a change in kinetic energy. And for this reason, in addition to the kinetic energy, we're going to define another value, which is called U uh, is equal to the potential energy. And then U, change in U as A goes to B is going to be negative the work as A goes to B is equal to U B minus UA. So basically, what this did was we have uh, uh, K delta K equals work. Uh, so what we have instead now is delta K plus delta U is equal to 0, which means that when we talk about K plus U, this is equal to some constant which we're going to call the energy. And the potential energy is just the work that can potentially be done by a force that we're talking about. So uh, delta K is also defined as negative delta U is equal to U of some position minus U of some initial position. So this is basically the same thing that we were doing last week. We just added another term, or we didn't even add another term, we just defined another term, which is related to the work, which is going to give us the potential energy. So instead of talking about the exact work done and calculating that every time, we can just talk about the potential energy of the system at any given time. So, for example, last week we saw that if we had a force of negative mg, then the work done would be equal to negative mg y final minus y initial is equal to negative mg times h, where h can be positive or negative, but it just refers to the height at a given time. So if this is the case, then we can define u as being positive mgh, where if we're talking about that constant force mg, then the potential energy at any given point, if we talk about like a water tower, then the potential energy at this point is going to be mgh, taller than the potential energy at the bottom point. So U equals 0, and then U equals mgh. And then another thing to note is that it doesn't matter, it doesn't matter where you place your 0 point, because what we're really talking about is the change in potential energy. So it doesn't matter where you say the 0 point is for uh your energy, it's still going to give you the same change in potential energy, which corresponds to the same change in kinetic energy. So you can also have this top part be equal to U equals 0, and this bottom part equal to U equals negative mgh. And that's going to give you the same delta U of mgh from the top to the bottom. So no matter where you put your 0, all you're caring about really is the delta U. So you can put it at the top of the tower, you can put it on the ground, you can put it in the center of the earth. Even though if you put it in the center of the earth, then this equation breaks down because as you saw in the midterm, or as you saw in exam 1, the force due to gravity isn't actually equal to uh, or the acceleration due to gravity and the force due to gravity isn't exactly equal to a constant. It's equal to some value dependent on r. So what the way that we define that energy is by setting r equal to infinity for our 0 point and seeing what change or where in space uh, or where what change in delta U is going to be responsible for a change in kinetic energy at any point in space compared to the initial U being 0 at r equals infinity. So this approximation is only good close to the surface of the Earth or the surface of a planet or a moon or something that has basically a constant g. But we're going to just say that you can set your 0 point equal to 0 wherever you want. So you can set 0 point equal to 1 million joules lower than the point at the ground, say, is what I'm trying to get at. So the other major point I want to get at is if we have F equals negative kx squared, then that gave us the work is equal, oh, sorry, not, I just kind of spoiled you. So if F equals negative kx, then work is equal to negative 1/2 k x squared minus x initial squared, which if we choose x initial squared to be our 0 point, goes to negative 1/2 k x squared, or positive 1/2 k x squared equals u. If we choose our initial point, if we choose 0u to be at that initial point x naught, if we choose zero potential energy, if we choose to zero out the potential energy at that point, x equals x naught. Okay, so that's pretty intuitive, I think, based on what we were doing last week. The only main problem that you might have is that if you have multiple forces acting on the system, how do you tell which potential energy or which work to do based on the system? And then, or which work is being done on a more complicated system? Say if you have a spring and a mass at the same time, or spring and gravity at the same time acting on the same object. So if this is the case, then U total is just going to be equal to the sigma, this sum of U, uh, I'm going to call them I, which is equal to U, the energy from the gravity plus the energy from the spring plus any other energies that might come up, any other forces that might uh, or any other forces that might be adding potential energy to the material. So if that's the case, then yeah, we just have K plus U total is equal to a constant, which we're going to call the total energy. Okay, so does this make sense so far?
Professor,
Yeah,
at the bottom, it's I think is that K plus U total equals the constant E?
yeah.
Okay. And
Okay, so is that the only question?
yeah, and also it says if we were to choose 0 point at x equals x naught.
Yeah. So, the work between we don't even have to choose 0 point at x equals x naught. We can just so work equals delta U equals 1/2 k x squared minus 1/2 k x naught squared. So this is actually wrong. This is unnecessary to choose the 0 point at x naught. So for uh we choose the 0 point at x equals 0. So if we choose the 0 point at x equals 0, then the change in potential energy is just going to be 1/2 kx squared minus 1/2 k times 0 squared, which is just going to be 1/2 kx squared.
Sorry, 1/2 k times x times 0.
Yeah, if that's going, or not x times 0, x equals 0 squared.
Okay.
So if we like the same way that I chose, you can either be 0 at the top or the bottom. Uh, this is just choosing the zero to be at x equals 0. So any change of from x equals 0 is just going to be x squared instead of x squared minus some naught x naught squared.
All right.
Okay, so let's actually save that version rather than this version. Uh, so this is called conservation of energy because the total energy is always going to be uh the total energy K plus U is always going to be the same uh no matter what materials we talk about, what forces we talk about, it's always going to end up being the same as long as we're talking about conservative forces. So what is a conservative force? So a conservative force is a force where if you make where U is dependent only on uh initial and final positions and not the path you walk to get there. Uh path let's just say walked from uh A to B for conservative forces, which is if you want a potential energy or you want to define a potential energy, all potential energies in this book, and depending on how you define it, are going to be from conservative forces. So what this means is that A to B uh, path 1 uh, for any path 1 F dot dl is equal to the uh, integral the path from any other path from A to B for F dot dl. So that's just stating what I stated earlier in mathematical terms. So uh, basically, if you go from here to here, it's the same thing as if you are going from here to here. So path 1 and then path 2. So if you do that and you get the same answer, then that means that uh, delta U path 1 is equal to delta U path 2, which means that U is only a function of uh, initial and final positions. in which case as well, if we make a circuit around any path, f dot dl, if we go all the way around path 1 and then we go back from path along path 2, and then we make a circuit, which is what this circle indicates on the integral, then that is going to give us a to b, let's just call it path 1, f dot dl, plus b to a instead of a to b, path 2, f dot dl, which is going to be equal to a to b p1 f dot dl minus a to b p2 f dot dl, because you're just going in the opposite direction. So you're going from a to b along one direction, which means that as you go along the opposite path at any given point, dl is going to be pointing in the opposite direction as if you were going from a to b when you're going from b to a. So this is just equal to a to b path 1 f dot dl minus a to b path 2 f dot dl, which is equal to 0. So that's a good way to test whether or not force is conservative. But forces are not always conservative. If force isn't so a force that might not be conservative include friction, and air resistance, because those are always going in the opposite. Those forces are always a resistance, because those forces are always going in the opposite direction of dl. No matter what path you go along, the force of air resistance or the force of friction is going to be pointing backwards along the path, which means that as you go in a circuit, it's just going to be the length of the circuit times 1 times whatever force was being exerted over the time, or whatever average force was being exerted over the time. So uh f so if we talk about fk dot dl, then fk is going to be always pointing in the opposite direction of the int, or the dl. It's always going to be pointing in the opposite direction of the path. So this is just going to be equal to negative fk, the magnitude, times dl is equal to negative fk times length of path. So as you go in the circle, that isn't going to equal zero, therefore it's a non-conservative force. But another thing to note is that even non-conservative forces are conservative. It's just that we're not talking about the forces in a microscopic level. We're not talking about like thermal heat. We're not talking about chemical energy. We're not talking about energy going from the system, from the object into the ground. So the energy goes from the object into the ground, and then that's going to give you uh yeah, that's just going to give you conservation of energy, but the energy is being transferred from one part of the system to another part of the system that you're not looking at. So if you're only looking at the object, you lose track of the energy from the that's being taken away by the frictional force, even though that frictional force is just changing the energy from the energy of the object to the energy of the ground. And then there's something else I want to bring up. Oh no. Um, yeah, there's something else I wanted to bring up. I can't remember what it is, so we're just, and it's not in my notes, so I don't think it's that important, but I just had like one sentence that I wanted to share that isn't coming to mind. So sorry about that. Do you have any questions about this path dependence and conserved versus non-conserved forces?
Professor,
Yeah.
so this equation at the very bottom here, this is specifically in the case of forces that aren't conservative, correct?
Yeah. Oh, yeah, that's for non-conservative forces. So if that's the case, if you go along a circular path and it doesn't equal zero, then it's a non-conservative force.
And D of L, that represents what exactly?
Oh, DL is just is the infinitesimal uh direction and length of the path. So it's just where the path is going. So as you integrate uh DL, then it's just going to take you along whatever path you're looking at. So it's if you're just going in one direction, it's dx or dy, but we want to just say dl because uh we want to say DL so you can have these more complicated paths and not worry about just going in the X or Y direction, but going in any direction that you choose.
Okay.
Oh, and then I think I remembered it. What I wanted to say is that U equals negative or force equals negative du dl. So for one dimension, this goes to negative du dx for one-dimensional movement, for one-dimensional uh for one-dimensional potentials in the x direction. So it would also be dy d or du dy for in the y direction. Okay, so I think that's what I wanted to say about that subject. And then as that is actually the main meat of the lecture. I'm just going to do some examples until we get to uh, a couple of examples, and then we're going to get to U diagrams, so potential energy diagrams, and what that means for the motion of the object. So this is the important part of the lecture. This is just like bringing up conservation of energy for the first time, which is going to be like really important. But when we get to uh, potential energy diagrams, that's also going to tell us how to work with this conservation of energy. So let's talk about a box on a spring being pulled down by gravity. So that C is way too long, but it's going with some velocity at point B, and it's going with no velocity at point A and point C. So in order to find the distance that this box stretches, we set total energy of point A is going to be equal to total energy of point C. So we set U spring and of A equals U gravity of A equals 0. So we just set both of these equal to 0 at the highest point at point A. So if that's the case, then 0 plus 0 plus 0 equals E total of A is equal to 0 because this is the kinetic energy. So we have point A where there's no kinetic energy because it's completely compressed. It's as compressed as it's going to be, and it's about to fall back down. And then point C has no kinetic energy because it's stretched out as it's going to be, and it's about to be pulled back up. So K of A, this is going to be K of C, is equal to, or not equal to, plus 1/2 K YC squared minus mg YC. Because we start out at a high, we start out with a 0 point at the high point, which means that the potential energy at the bottom is going to be equal to negative mgyc. So 1/2 K, where YC is just the absolute value of this height, C squared equals mg YC. So YC is going to end up being, oh, actually, yeah. Let's just instead of saying absolute value, let's just say YC is a negative value because YC is going in the negative direction. I forgot my own rules for a second. So YC 1/2 K YC equals negative mg. So YC equals negative 2 mg over K. So that's going to be how much this spring stretches out just based on gravity and the force of gravity versus the force of the restoring force, the force of the spring, based only on kinetic energy, not doing anything about the forces that you're setting forces equal to each other or anything like that. So that's going to be the first part of the problem. The second part of the problem is this YB is halfway in between YC and or YC and YA. So this is equal to YC over 2. So if this is the case, then finding the kinetic energy at this point is going to be EA equals EB equals 0. So this is equal to KB plus 1/2 K YC over 2 squared plus uh MG YC over 2. So KB is equal to negative 1/2 K YC over 2 squared plus MG YC over 2 is equal to negative 1/2 K. Oh, yeah, sorry. That should be a minus. K YC over 2 squared minus MG times YC over 2, which is YC equals negative 2 mg over B or over K. So negative 2 mg over K times 2 squared minus mg times negative 2 mg over K times 2 is equal to mg squared over K minus 1/2 K times mg over K squared is equal to 1/2 mg squared over K. So this is equal to the kinetic energy, which is equal to 1/2 mv vb squared. So this is equal to, this gives us vb squared is equal to m over k times g squared. So vb is equal to square root of m over k times g. So that gives us the maximum value. So the book doesn't do a very good job of explaining this, but uh if you're directly in between you're at the middle point between A and C where it's either completely depressed or completely compressed or completely stretched out, then that's going to be your maximum value of V. So the maximum value of V is going to be equal to square root of M over K times G. Any questions about this problem?
Professor.
Yeah.
So this equation right here, this is specifically dealing with the you said, is this the maximum potential energy of B?
No, this is the maximum kinetic energy of the system.
Okay. Of B specifically.
Yeah. So at point B, so there can only be one kinetic energy at any of these 3 points, but B is going to have the maximum kinetic energy of any point uh because it's halfway in between being totally compressed and totally stretched out. So it's at the point where it is neither compressed nor stretched out. So uh because it's at this point, there's basically no uh force. Uh yeah, the forces cancel each other out, so it's being no, that's not true. Ignore that part. Uh yeah, it's going at its maximum value of kinetic energy because all of uh the spring isn't compressed and it isn't uh stretched out. Therefore, it's not going to, or it's going to be going the fastest it goes because there's no force on the spring pulling up or pulling down.
Yeah.
Or yeah. Any other questions?
In the I think earlier in the up in the equation on the screen in KB equals, I think that's in the parentheses, that's is that Y of C over 2?
Yeah. So it's in the halfway point between point A and point B.
Okay, and YC represents the height of the total amount that can be stretched.
Yeah.
Okay.
Yep. Okay, so uh I'm just going to take a brief detour and say uh look at this different all these different numbers for energy of different potential energies or different kinetic energies. So the Big Bang is 10 to the 68th power. Then the world energy use is 10 to the 20th power, which is makes sense because the world is so much smaller than the entire universe. All the energy in the universe is going to be like 10 to the 48th power, bigger than all just the energy that we're able to use. Uh, there's some fusion bombs, Hiroshima bombs, crude oil, TNT, gasoline, and then 2,000 calories is about 1.2 times 10 to the seventh. And then tennis ball is about 22 joules. So a joule is around the range of stuff that we see in real life, or just the stuff that we see when we're doing like physics experiments with uh small masses. So like what you see when we're talking about work and energy in the lab would be around 1 through 20 or 100 joules. So it's pretty close, or it's pretty close to 1 joule is how we define that term. And then a mosquito has 10 to the -6 energy in it, and then the energy to break one DNA strand is 10 to the -19. So about as big of a difference between the energy to break one DNA strand uh, to the annual world energy use as there is between the annual world energy use and the Big Bang. So logarithmically, that's not a huge difference, but if we talk about just linearly, then that's about 100 million times, or yeah, 1 billion times more energy. The ratio between the Big Bang and the world energy use is about 1 billion times bigger than the difference between the world energy use and the energy to break one DNA strand. So that just gives you a scale of like how big the universe is, basically.
Professor,
Yep.
is it true that the universe is getting less and less hot?
Yeah, so the universe, I'm not an astronomer. I did all of my work in condensed matter theory, but that makes sense to me, or condensed matter experimentalism. So that makes sense to me as the universe is spreading out and becoming more disordered. So as it becomes more disordered, then that means that there's less energy per particle, or like the energy is less held together in thermal energy and is more held together in other types of energy. Actually, let's. I'm going to define something that you might not even learn this entire class. You might not learn this until 2AG. But entropy is equal to ds equals uh dq over t. And then entropy in the universe is always going up, which means that as there can be no so as entropy in the universe is going up and there can be no change in dq over the course of the universe, then uh that means that temperature has to be going down in order for dq over t to be going up. So yeah, that makes sense just from this entropy perspective. I don't know how to explain it from another perspective, but uh, when you learn entropy, you've probably heard the term entropy and you've heard that it goes up, but entropy is proportional to 1 over T. So as entropy of the universe goes up, then I think that the average temperature of the universe has to go down. So does that satisfy you? I think that I'm not a cosmologist, so I don't have a better understanding of the overall, like the specific forces going on in the greater universe. But doing that uh does seem to check out that the universe needs to get smaller or colder in order for the entropy to go up.
Yeah, that makes sense.
Yeah. So I have never actually seen this equation before, but so I'm going to try deriving it. Okay. Instead of deriving it, because I think that would take like 10 minutes, I'm just going to say what the book says about it. Is that f dot dr is equal to fx dx plus fy dy. And in order for this to be the case, in order for this to be an exact differential that just resolves itself so that if you go in a circle around it, it equals 0, then dfx dy must be equal to dfy dx. So that's just I don't think this is entirely important. I'm not going to bring it up. I don't think anywhere in class unless it they do something really weird in the future chapters where this does become important, but I've never seen this before. I'm just including it in case it ends up being I'm including it in case it ends up being something that you need to use for future professors' classes. And then, like I said, F equals negative du dl equals negative du dx I minus du dy j. And then work non-conservative from AB is equal to delta k plus u from AB is equal to delta E from AB. So these are just a few of the equations. I already went over the details of how this works, but these are just a few specific equations that the book has, so I decided to include them in the lecture. And then, oh yeah, the other thing that I want to bring up is that if forces do no work, they have no they have no potential energy. So if you have normal force acting on a block and it's moving this way, then N dot dl equals 0 yields no change in energy. So this might seem kind of pointless right now, or like a no duh thing, but it is uh something that comes up when we're talking about magnetic forces, because magnetic forces are always going to be perpendicular to the direction of velocity. That means that they do no work, which means that no matter uh what type of magnetic like even as a magnet pulls up like a car, it's not actually doing work. The battery's the thing that's doing work. It's just redirecting the direction of force, basically. Or it's redirecting the motion of the particles. Uh, Even though there's no force dot dl, that's going to cause a work or a change in energy. So another thing that I'm just going to steal completely from the book is the problem solving techniques for conservation of energy, which are basically identify the body or bodies to be studied, the system, identify all forces acting on the body or bodies, determine whether each force does work, that does work is conservative. If a non-conservative force is doing work, the mechanical energy is not conserved and the system must then be analyzed with non-conservative work. So like I said, if you have friction, then that's going to cause a change in energy, which is going to cause a change uh then which means that you can't just use conservation of energy in a non-trivial way. And then for every force that does work, choose a reference point and determine the total potential energy function for the force. The reference point for various potential energies does not have to be the same location. And then apply the principle of mechanical energy conservation by saying the sum of the kinetic energies and the potential energies equal at every point of interest. So, uh, let's do one problem that is going to it's not going to not necessarily going to pop up on the exam, but if we have a simple pendulum that's swinging from left to right, then what is going to be its velocity uh as it's passing through the lowest point of the as it's passing through the lowest point of its swinging. So you have theta, you have L, and then the length of the pendulum. So first thing we want to do is that say that E at point A is equal to E at point B. And then since this is the highest point of the pendulum, there's no kinetic energy working on it, or there's no kinetic energy in the system. So 0 K plus MGH, where H is defined as the height between this one and this one, point A and point B, is equal to 1/2 MV squared B plus 0. So VB squared is equal is going to be equal to sorry, 2GH. So VB is equal to the square root of 2GH. So that's pretty simple. That's just basically going to be any conservation of energy problem where the only force is gravity. But how do we define H if we're talking about the angle between if we're talking about some angle and some length of some non-changing length of pendulum? So the way that we do this is seeing that the projection that the pendulum makes along the y-axis at any given time is going to be equal to L negative y equals L cosine theta, right? Because it's going to be the adjacent over the hypotenuse is cosine. So y is equal to negative L cosine theta. So as we go from theta to equals 30 degrees or whatever value we have for theta there, to theta equals 0, then y just goes to negative L. So H is going to be equal to H is equal to negative L cosine theta minus negative L equals L times 1 minus cosine theta. Plug that back in, you get VB equals square root of 2G L times 1 minus cosine theta. Okay, so that's just a standard problem that I want to bring up because it's a standard problem. But this value, this L, is pretty yeah, this value that you get for a pendulum is pretty useful for future problem solving methods. This height as a function of L and the length and the angle is going to be something that you are going to need to know at some point for future problem solving. Okay, so that is uh the main uh thing that or the simplest problem that we're going to go through. So as we also do this, we have K equals 1/2 mv squared equals E minus U of X. So if we want to solve V at any given time and we know the V and we know the energy, then we can say V equals the square root of 2 over M E minus U of X. So that tells us the velocity at any given time. That's pretty simple to do. So uh, in our early in what we were doing earlier, where uh, L time 2G L times what did we come up with? Yeah, 2GL times 1 minus cosine theta. Then that just told us the total energy minus the energy at U of X, or minus the energy at the bottom of the well. So this is the same form as uh that velocity that we just got. We're just making it to a more generalizable form. And then if we do this, then we can also do dx dt equals square root of 2 over m e minus u of x. So dt is going to be equal to dx divided by square root of 2 over m e minus u of x. Which means that t is equal the time that it takes to travel along any path, given just the energy and just the potential, is going to be the integral of dx over 2 over m e minus u of x uh, times dx and integrated. So let's do this for a pretty simple problem. Or a pretty simple energy where energy U of X ah, is equal to negative E times X over X naught. So if this is the problem, then T is going to be equal to dx over 2 over m E minus plus E times X over X naught. Which if we do the integral of this is just going to be so let's actually do the integral. Let's not be lazy about this. Equals 2 over m e times 1 plus x over x naught. I think they made a typo. Yeah, I think this is supposed to be e times x over x, not minus e. Equals square root 2x square root of 2 over m x naught 2e over m x naught x naught minus x dx. Uh, set x, set a new, do a u substitution, x u equals 2e over m x naught minus x. So du equals negative 2e over m x naught dx. So this time becomes negative m x naught over 2e du over the square root of u equals negative m x naught over 2e to negative 2 times the square root of u, which is equal to m x naught over e square root of 2e m over x naught minus x evaluated from x naught to x, which is just going to be equal to 2 square root x naught. Oh, sorry. 2 square root x naught minus x over the square root of 2e over m x naught. So when we solve for t, so when we solve for x naught, this gives us x equals x naught minus 1/2 e over m x naught t squared. So this is just the equation for acceleration with e over m x naught being the acceleration. So yeah, that was pretty exhausting, but it did get us, it did tell us that this potential energy or this potential energy is going to give us the total energy of, or it's going to give us the energy for constant acceleration, where constant acceleration is E, the energy at any given point divided by m times the position at that point. Or at the initial point. So, what do we do when we're so we know what how it works to talk about this mathematically, but how about graphically? So what I'm going to do is I'm going to draw out where'd it go? Where'd my whiteboard go? What? No, let me back on my whiteboard. X, U. I'm going to draw out a diagram of U versus X for a quadratic equation, so for a spring type equation, so if this is the case, then we have some constant E, and we're going to find that the particle can never cross this E line. It can never be higher than E, because yeah, because of conservation of energy, the total energy of the particle can never be higher than E. So if that's the case, then or it can never be higher or it can never be lower than E. So if that's the case, then this difference between E and the line and the potential is equal to K, and E and between the potential and the x-axis is equal to U. These are the turning points where, because there's no K value, there's no potential there, or there's only potential there. There's no K value, there's no velocity. So since there's no velocity, it can't go any farther than this X value. Therefore, these are turning points where it starts going backwards and starts going down the slope. This is, and then this is the equilibrium point. Where x naught equals 0. And yeah, let's just define this formally. Ux equals 1/2 kx squared. So this is the equilibrium point. And that's equilibrium because du dx equals negative force is equal to 0. So if there's no force, and your particle is at that point, then the particle is experiencing no force, and if it's left, if it has no potential or kinetic energy, then it's just going to stay at that point forever, which is why it's called an equilibrium point. So x max in this case is 1/2 kx squared. X max squared is equal to U, which is equal to the energy. So X max is equal to square root of 2e over k. And then V max has when 1/2 m v squared is equal to E, because there's no potential energy at this point. So V max squared is equal to square root of 2e over m. And then yeah, so at the bottom of the potential well at the equilibrium, U equals 0, so E is entirely kinetic energy, which means that this equation holds true. And then what about a more complicated uh drawing like this, where u of x equals 2x to the fourth minus x squared. So if this is the case, then if you have an e that's lower than an equilibrium point, so even though there are 4 points that are it's possible to turn around at, if we look at this graph, this point, whatever particle is in here can't get above any of these points. So it's actually going to be if it is stuck in this well, or if it starts out in this well over here, it's going to always be stuck in this well. And if it's because it can't get over to the other well, so even though there's a turning point at a much higher x value, it can't get there. Therefore, it's stuck with these turning points over here. And then let's just say that -1/4 is e. So k equals e minus u is greater than or equal to 0, because this is always the case, because you see that we chose a u where u was going to be equal to less than 0 at many points, but because k is v squared, v v squared can't be less than 0 because it's a squared. So our values, in order to find the allowed places where it's allowed to be, where the particle is allowed to exist before it has to turn over, we have k equals e minus u is greater than or equal to 0. So this is -1/4 minus 2x to the fourth minus x squared is greater than or equal to 0. Uh, this simplifies to 2x squared minus 1/2 squared is less than or equal to 1/4, which means that x squared is greater than or equal to 1/2 minus square root of 1/8, or less than or equal to 1/2 plus square root of 1/8. So I didn't really go through the algebra there because I've been talking for like 2 hours, and I feel like some of you want me to a lot of you probably want me to finish up, but this gives us the values for x squared where it's allowed to be. So these turning points are at 1/2 minus the square root of 1/8 and 1/2 plus the square root of 1/8. And then the equilibrium points are du dx is equal to -f is equal to 0. So du dx equilibrium is equal to negative 2 times 4x cubed minus 2 times x is equal to 0. 2x squared is equal to x, or 2x squared is equal to 1. X is equal to square root of 1 over 2. And then are these, the way to find out whether these are stable equilibrium points or unstable equilibrium points is to take the second derivative. And if the second derivative is negative, then it is a relative maximum, or if the second derivative is positive, then it's a relative minimum, which makes sense because if the second derivative is positive, then it's going to be curving upward. Then it's a relative minimum. And then if the second derivative is negative, then it's a relative maximum and it's unstable because the force will be pushing, force equals negative du dx will be pushing out from that equilibrium point rather than pushing in on the equilibrium point. So df dx equals negative d squared u dx squared is equal to negative 24x squared plus 4. So what we want to do is if second derivative is negative, then that means that df dx is positive. Which means that the force is going to increase as x goes out of it, or the force is pushing, yeah, it's pushing the material out of, it's pushing, sorry, I've been talking for a while. If df dx is positive, then that means that the force is going to be pushing the particle, the object, the whatever, out of the, yeah, out of the equilibrium point. And if it's negative, then it's going to be pushing it back towards the equilibrium point as it goes out. So what we want to see is if df squared or df du, or sorry, if the double derivative of u is positive, is unstable equilibrium. If is negative, is stable. So the double derivative of u at this point, at x equals square root of 1/2, d squared u dx squared at equilibrium is equal to 24x squared minus 4 is equal to 24 times 1/2 minus 4 is greater than or equal to 0, or is greater than or equal to 0, which is going to be 8, I believe. Yeah. So this is a stable equilibrium. So there's a lot of stuff about different types of energy that I can just quickly bring up, go through in a couple minutes. But the main thing that I want to do is just one more problem where uh, if we have a potential energy that's 1/2 k x squared equals u, then t equals x naught to x dx over square root of uh, k over m 2e over k minus x squared, which is, if we plug it into Wolfram Alpha or we plug it into a table of integrals, is just going to give us square root of m over k arc sine x divided by 2e square root of 2e over k minus arc sine x naught square root of 2e over k, which gives us, if we rearrange the variables, if we do algebra to it, x of t equals square root of 2e over k times sine square root of k over m t plus 90 degrees, because sine of because 1/2 k x naught squared equals e. If we're treating x naught as the farthest point away, then x naught over square root of 2e over k is equal to 1. Is equal to 1. Therefore, sine -1 of 1 equals 90 degrees. So when we plug this in, it's sine of square root of k over mt plus 90 degrees, which is square root of 2e over k times sine, or not sine, cosine of square root of k over m times t. So that is the last thing I want to leave off on. So I just want to say that what this proves is that using conservation of energy, not using like double derivatives or like differential equations or anything like that, we just proved that x of t is going to be dependent on t to it's going to be a harmonic motion, and it's going to be dependent on t uh by a sine or a cosine wave with the angular frequency given by square root of k over m. So this is just an interesting thing to note. We can intuitively understand that it goes farther out the farther out it goes, the more force is pushing on it, so the more kinetic energy is taken away. So it does that, and then the particle moves back once it reaches its maximum value. Then it goes there, moves back once it reaches its maximum value, moves back once it reaches its maximum value. Uh, so we understand that it oscillates back and forth, but with this, we know exactly how it oscillates back and forth. It oscillates as a sine wave, and it oscillates with an angular frequency of square root of k over n. So this is a very important understanding as you get on with as you take like higher physics classes. And then just last thing I want to do is just go over the quickly go over the different types of energy. I'm just going to read directly from the book because, like I said, I've been talking for like 2 hours and I feel like you must want to get home at this point. So, I'm
It's
going
okay,
to,
Professor. I already am home.
oh, yeah, you as well as everyone who's watching the recording.
That's okay.
Yeah, but yeah, I'm home too. That's why I have a bookshelf and a closet in the background. Yeah, so sources of energy, uh, in addition to like the mechanical energy that we've been talking about, just like potential energy and kinetic energy, then there's also different types of energy called thermal energy, which is the atoms and molecules inside of objects just acting, moving around by themselves. So this is related to temperature, so it's called thermal energy. We have electrical energy, which is based on electromagnetic force. Uh, uh, Fuels such as gasoline and fuel have chemical energy, which is potential energy arising from the molecular structure, which is then broken down and released into mechanical energy or any other type of energy. And then light is electromagnetic radiation or radiant energy that includes radio, infrared, ultraviolet, X-rays, and gamma rays. And then all bodies with thermal energy can radiate energy in electromagnetic waves. And finally, they have nuclear energy coming from reactions and processes that convert measurable amounts of mass into energy. Nuclear energy is transformed into radiant energy in the sun, into thermal energy in the spoilers of nuclear power plants, and then into electrical energy of the generators of power plants. So all of this basically comes from the sun, except for like nuclear. I mean, I guess the materials that the Earth is made from also come from the sun or from space. So technically, nuclear energy also comes from the sun, but the sun works on nuclear energy, uh, which releases radiant energy, which releases thermal energy. Uh, it does electrical energy to a certain extent, but mostly that is just a property of the matter that you're looking at, and then chemical energy is also just a property of the matter that we're looking at. And then there's some stuff that I recommend looking at if you're interested in like what energy means to like non-physics class. So like the different ways to conserve energy in a non-physics definition of conservation, because all energy is conserved in a physics definition of conservation, but it's not useful energy for it's not going to be useful energy for uh us anymore, so it's not conserved in a non-physics ideal of what energy is and what energy conservation is. So if you have any questions about like energy conservation and like how the world works, then there's from page 369 to page 372 is just a few pages talking about that and like talking about like practical applications of what we've been learning. But instead of just reading like 5 pages straight out of the book, I'm going to leave that to you to do. So do you have any questions before we end up finishing the class or finishing the lecture?
Um, no, I don't think so, Professor.
Okay. Yeah, hopefully that wasn't last week's lecture was about 40 minutes and this week's lecture was about 2 hours. So hopefully that wasn't too painful. But I'm glad that you're here. It's like really useful to have uh sounding boards and like not just be talking to myself. So I'm glad that you're here and that you stayed through the lecture. Thanks.
Thank you, Professor.
Mm-hmm. All right. Well, I'm going to stop recording and then feel free to leave when you want to.